Hey everybody! In the last unit, we had focused on lines, where we were talking about different ways that we can write the equation of a line. So we looked at vector equations, parametric equations, scalar Cartesian equations, and now looking at unit 4, you'll notice that planes also have similar ways of writing equations. And so in this video, lesson 4.2, we're going to look at how to write a plane's equation in scalar form. Okay, so this is going to be part 1 because I just want to show you how to write the equation itself. And then in part 2, I'm going to show you an application. Okay, so let's get into it. On the right-hand side, you'll see a plane that I'm just going to call plane 1. And then on that plane, which, I mean, you guys can see this plane as like a piece of paper. There are many different ways I can write or draw arrows on the piece of paper. Okay, so you have infinite number of direction vectors that lie on this plane. In fact, 2 of them, if I wanted to, I could put them tail to tail, and I could actually find a perpendicular vector to this plane by doing the cross product in either direction. Okay, so you're going to get a normal vector, right? So this is going to be a normal vector, which is perpendicular, and depending on which way you decide to cross those direction vectors, you either get a normal that goes upwards or you'll get a normal that goes downwards. Now, I'm not sure if you can kind of visualize this. If, again, you drew a bunch of arrows on a piece of paper and all those arrows were your direction vectors, taking your pencil and placing it like your eraser onto your paper would then be, like, let's say your pencil is like this, they'll be perpendicular to every single arrow that you've drawn on your piece of paper. All right, so your normal is made up of an A, B, C, which are your 3 components of your normal vector. And I'm going to scroll down so I can show you this diagram. Let's just say that you have an original point on your plane, and I'm going to now do this in 3 dimensions. But we want to reach another point because there are infinite number of points on this plane. And I actually want to describe this one this one position vector in terms of a scalar equation. So that is my goal. My goal is to describe this specific position vector in terms of a scalar. Okay, now again, I can create a direction vector from one point to the other, and there should be a perpendicular vector, which is our normal, to that plane and therefore to that direction vector. These 2 are going to interact with each other, so the normal and that direction vector from P naught to P. Those guys, since they're perpendicular, they'll have a dot product of 0. And I can use that in order to create a scalar equation for OP. Okay, so that's all on the left-hand side. You'll notice that instead of writing P naught to P, I decided to break it down into each of the position vectors for those specific points. Okay, so you got OP minus OP naught, and I'm going to dot that result with the normal vector to make sure that it equals to 0 and basically prove that the dot product is 0. Okay, so obviously, again, dot products of perpendicular vectors are going to be 0. In the next step, I replaced everything in terms of the component form, and so you'll see everything in their ordered triples. Once I subtract these 2, I'll get one vector that I'll then dot with the normal ABC. And so you can follow all of the math. Eventually, what I'm going to have is AX, BY, and CZ that I just want to pull to the side. And all of the other leftover junk, I'm just going to kind of sweep under the carpet in brackets and label that as D. So that is our scalar Cartesian equation right here. Okay, so it's AX plus BY plus CZ plus D equals to 0, where your X, Y, and Z are all going to be a point that lies on the plane. And then the ABC is your normal vector. And so remember, just like in a line, each of these coefficients was your normal vector just embedded into the equation. Okay, so we can actually see right away what our normal vector is just by looking at the scalar Cartesian equation. So here is a note. You are not allowed to have any of your coefficients as a negative or as a fraction. Okay, so rather, okay, hold on. I don't know if I said that right. Let's try that one more time. Your A value, which is your leading coefficient, is not allowed to be a negative. I think the reason why is it just looks kind of ugly. And so we want to lead off on a positive note. Haha. Okay, so let's just bring everything to the other side of the equal sign if your x value is a negative. It'll help you to change everything to a positive. Also, again, no fractions and no decimals. You can kind of manipulate all of the numbers to not be a fraction or a decimal by multiplying the entire fraction by whatever your common denominator is for all of your fractions. Okay, so in other words, no negative coefficient, leading coefficient, and no fractions. Okay, so let's check out an example. Example number 1. Find the scalar equation of a plane. It has to go through a point, and they've really nicely given us our normal as well. And so the normal is, remember, our A, B, and C. So I'm going to place that into the equation. Our point, which is our x, y, and z, right here, is going to go into our x, y, and z. Notice that D is the only one left that is still a variable, and so I'm going to solve for that, and as soon as I have my D, I'm going to place it into the position of D. Our answer is a scalar equation, and so obviously we still want it in the form ax plus by plus cz plus our D equals to 0. The only thing is you won't see the blue x, y, and z. All you'll need to know is that your normal is still visible as your coefficients in front of your x, y, and z. Okay, so that is the final answer. It's not too difficult. It gets more difficult when obviously they don't give you the ideal situation where they give you a point and a normal vector. So let's take a look at that. Example number 2. Find the scalar equation of the plane, but they've actually just given you the plane. However, inside the plane, I can see a point, and okay, I don't see a normal vector, but I do see 2 direction vectors that I can take advantage of. Okay, so those 2 direction vectors I've rewritten on the left-hand side under our first step. If you take those 2 direction vectors, and remember that they lie right on the plane, so this is one direction vector, and this one is the second one. We can then do the cross product in order to find the normal. So the normal is going to be, whoops, not there, right there, perpendicular. Okay, so you can cross them in either order, it doesn't really matter. So I just did A cross B, and I got my normal. I'm going to use that normal as my A, B, and C coefficients in front of my x, y, z. I'm also going to use that random point that we have right here as my x, y, z. Solve for D, and then plug it back into the equation with your normal vector coefficients in front of the x, y, and z. Okay, so here's the thing. We had said before, no negatives as your leading coefficient. So this is a problem right here, which means that I would just bring everything over to the other side, and you would then get this equation right here. Okay, so that's nice. We have a positive leading coefficient. I don't see any fractions, and so that is exactly how I would want the answer. Now I do want to mention something. I'm going to get rid of this, all of this, so I can show you that if I decided to pull that negative out so that I get a positive as the leading number here, I'm going to pull out a -1, and you are always allowed to pull out scalar, I guess, common factors, a scalar amount, out into the front of the bracket if you wish to. So I'll be left with something like this, and I will get the exact same answer even if I use this direction vector, this normal vector instead. So let me show you. If I instead used my A, B, and C as these numbers, I'll get, whoops, well, I'm going to just jump into it because I don't have a lot of space. AX minus BY minus 3, not 3C, Z, and I don't know what my D is. Then I'm going to sub in that point, so 3, 1, and 2. Minus 8, that was minus 3 plus D equals to 0. I'll get a 3 minus 8 minus 6 plus D equals to 0. And what is that? Negative 14, negative 11. D will equal to positive 11. So in other words, I'll get my positive 11, my 1x, negative 8y, negative 3z. So I'll automatically go into that final purple answer instead of having gone to this answer first. So if you reduce by taking out that negative or that common factor first, you won't have to reduce it later on. You'll get the right answer at the very beginning. Okay, so reduce or don't reduce, it doesn't matter because eventually you'll have to reduce your equation. So I'll show you that again in this example. Example number 3 says find the scalar equation of a plane through 3 points. Oh man, they didn't even give us direction vectors this time. They gave us 3 points. Okay, we're going to find either like any point you want. That'll be the point that you're going to sub in as your x, y, and z for your scalar equation. You could have chosen q or r. It doesn't matter. But I do need a normal vector, which they didn't give us. And so we're going to have to find first direction vectors that we can do the cross product for. Okay, so I found this one by doing the direction vector of PQ. Okay, and then I also found this guy by doing the direction vector of QR. Okay, so I have 2 direction vectors now that I'm then going to do the cross product. So notice in step number 2, we did the cross product in order to find the normal, and notice that I did end up taking out a common factor of 3 because I noticed that all of these guys could be divided by 3, and so I'm just going to reduce it beforehand. I'm left with a nice normal vector that I can then put into my ax plus by plus cz plus d equals 0 equation. All right, but I will show you what happens if we do this one instead, and you'll notice that we get the same answer. Okay, so on the right-hand side, step number 3, we're then going to put in our point P with our A, B, C coefficients from our normal vector, solve for D, which I get negative 29, and then what I'm going to do is write everything again with the ABC normal vector and the D number now, and leaving alone our x, y, and z. So that'll be our scalar equation. But I did say, and I'm sorry to be kind of jumpy, I'm going to extend the page. What happens if we just leave it like that? Well, you're going to get your ax plus by plus cz, and I'll have to solve for my d again. We're going to put in the point. So the point was negative 3, 1, and 4. Okay, that's 3 plus 12 plus 21 plus d equals to 0. I need more room. Okay, negative 9 plus 12 plus, what is that, 84, and d equals to 0. Okay, that's what, 96, negative 9, 17, that's 87. Okay, that's a positive 87. 87 plus d, which means d is negative 87. So I'm going to rewrite this guy. Therefore, 3x plus 12y plus 21z minus 87 is equal to 0. If I hadn't reduced before, and I kept like the 3, the 12, and the 21, I would have gotten this equation. But notice that each of the coefficients and the constant at the end, they can all be divided by 3. And so if I divide by 3, I would then get x, 4y, 7z, and minus, what is that, 2 and 29. Okay, which is this guy right here. Up to you if you guys want to reduce beforehand or after. I think it makes more sense beforehand just because these are nice and small numbers right here. It gets a little bit more complicated later on. Okay, so here is the last part. What we're going to do is we're going to just talk about two planes. So as you can see them at the bottom, I have two planes, and we'll just call them plane number 1. And then we'll have this guy as plane number 2. We can tell if two planes are identical, as in they lie on top of each other, or they're coincident, by checking to see if their normals are scalar multiples of each other. First of all, they could have scalar multiples of their normals. So let me just draw both normals. This one has a normal that goes this way, and this guy has a normal that goes this way. Okay, so we'll just call this normal 1 and normal 2. If they're parallel, they will be written like this, as scalar multiples. And if they're parallel, that means that the planes are parallel. But it doesn't necessarily mean that they're coincident. And so we have to go on to the second step as well. So the first step is just to see if both the planes are parallel to each other, but they could be distinct or they could be coincident. And so the second step right here is to check whether or not they are actually coincident. And that's if you choose one point somewhere on plane 1 and you sub it into plane 2, if it does exist on that other plane as well, then they must be coincident. So let's take a look at what that kind of a question looks like. Whoops. Okay, so example number 4. Determine whether or not plane 1 and plane 2 are parallel. When they say parallel, technically parallel and coincident are both parallel. So I'm just going to specify that this one is talking about parallel and distinct. Or if they're coincident, or if they're neither. So number 1 is saying, well, we want to make sure that they're actually not neither, and we do that by seeing if they're parallel. So going into plane number 1, what I'm going to do is I'm just going to check both of the direction vectors. Okay, once I have the direction vectors, I can then find the normal vector, which is this guy right here, nice and reduced, because I pulled out that common factor. So it's nice and small. Then what I'm going to do is I'm going to compare it to the normal vector of plane 2. And it's not in the same form, but I can easily see each of the parts of the normal vector because they're the coefficients in front of that scalar form. So I get something like this. Now when I compare both of these guys together, this guy and that guy, they're pretty much the same. And if they're the same, that means they're parallel. So we've now gotten rid of this case, and all we have to do is make sure that they're either distinct or they're coincident. So I'm thinking we need to find a point that is on plane 1 and sub it into plane 2. If that works, they're coincident. If they don't, then they're distinct. So it does look like I have an extra point that I can probably deal with. This guy right here. Let's take that one and sub it into the other equation. Okay, so I'm going to take point 1 from plane 1, which is the 160. I'm going to sub it into plane 2 and see if it somehow works. And when I say works, I mean you should be able to tell if when you sub it in, something is balancing or something is working correctly. And so when I subbed it in, I'm noticing that I just did a left side, right side check. Both the left side and right side match, which means that that point, the purple point, is on the orange plane. That tells me that they're parallel and coincident and not distinct. Okay, so we've actually gone over a little bit of how I guess planes interact with each other. And as we continue on through this unit, we'll start to do some more interaction kind of videos. Have a great day, guys.